Welcome to Calculus 1 class. Today we're going to talk about the preview of calculus, kind of give an overview what the calculus is really about. So here I wrote the concept that calculus is the mathematics of change. Okay, when you think about calculus, you think about the word change. For example, calculus involves with velocities, accelerations, tangent lines, slopes, area, volume, arc length, centroids, curvatures, variety of other many concepts that have enabled scientists, engineers, and economists to model real life scenarios. Calculus is really the fundamentals for these higher mathematics. It's very basic foundations for many higher level math courses. Where the engineer, scientists, they can actually use calculus for a lot of real life scenarios. And if we ever get a chance in these recordings, we will do some application problems. That will kind of give us a better idea how calculus is worked in real life scenarios. Alright, now a lot of times we see some of these same type of problems in pre-calculus mathematics. Okay, the biggest fundamental difference is that calculus is actually a lot more dynamic dealing with these type of problems. For example, we can actually use calculus to analyze the velocity of an accelerating object, slope of a curve. That's very interesting, because what we know about slopes is slope of a straight line, but how do we find the slope of a curve? And how do we normally find, and how can we find the areas under a general curve? We can find area under a, we can find the area of a rectangle, a square, but how do you find the area of a curvature? Okay, and these are involving with calculus. Alright, calculus is a limit machine. It actually reformulates the pre-calculated mathematics through the use of a limiting process to form calculus. So far, we have learned a lot of pre-calculus materials. Before we can reach the actual calculus materials, we're going to learn about the limit process. Okay, and that's what the next few recording will be regarding. All right, the notion of a limit is fundamental to the study of calculus. One of the most basic example of limit is called the tangent line problem. In the tangent line problem, let's say we're going to have a function f and a point on the graph, and the question asked to find an equation. We need to find an equation to the tangent line at a point P. So basically, well, let me make this a little bit smaller, a bit too tall. Alright, so basically what we have is a curve. So let me just draw a curve. If I have a curve, and on the curve there's a point P. Let my curve a little bit higher. Let's say there's a point called a point P. Alright. What is called a tangent line. A tangent line is actually a line that will only touch my curve at one point. So I'm going to draw a line that will only intersect my, didn't draw very well, excuse me, that will only intersecting, that will actually only touch my, do it right there. Tell you what, I'm going to put my point, I'm going to slide my point P slightly over here. Okay, try to draw a little bit pretty. Tangent line is a line that will only touch my curve at one point. Okay, that's called a tangent line. Alright, so what we want to do is asking to find the equation for this tangent line. Okay, I need to find the equation for this tangent line at that point. Now, because a tangent line only intersecting at the curve at one point, I kind of need 2 points to actually formulate, okay, some type of equation for this particular straight line. So, except for cases involving a vertical tangent line, the problem of finding a tangent line at point P is actually equivalent to find the slope of the tangent line at that point P. And the slope of the tangent line can be approximated by using a line through the point of tangency and a second point called Q on the same curve. And that line will be called a secant line. So I'm going to use the same picture here. So I already draw my tangent line. I'm going to bring it over here. So let's say we pick another point called Q somewhere along this curve. This is your point Q. Alright. And we're going to draw another line that will cross this curve at 2 points. And that would be called a secant line. Like I said earlier, to find the slope of a line, well, you gotta find to find the equation of the line, you gotta have a slope. If we need a slope, we gotta have 2 points. So that's why I have another point Q. All right. So this line is called a secant line. Alright, now what I wrote here is if the point P is C comma F of C. Okay, now the F is referring to the function is F. Okay, a C is referring to the X value of the point P. So at point P I have some sort of, I'm gonna do it this way. I'm gonna write it right below it. So at this point P, okay, every point on the X and Y axis has some sort of X value and the Y value. So let's say we call this X value C, and its Y value will be substitute this X value into the actual function. So we can abbreviate it as F of C. Okay, when you substitute an X value into the function, the output is actually the Y value. Alright, so my point P has some sort of X value and the Y value. And let's say the second point Q is C plus delta of X. Okay, we call the delta of X is because from this point P to the point Q, there is a change of displacement. From this point, keep going out, okay, from this X value to the X value of a Q, okay, this distance is called the changing of displacement, or we call it delta X. Alright, and the Y value of a point Q and the Y value of point P, okay, their differences, okay, will be changing of the Y, or changing the altitude, or delta of Y. Now rather than write delta of Y, I'm going to use the symbol I already used. So I'm going to draw another line going up. Okay, so the difference in the Y value here will actually be F, oops, sorry. It'll be F of C plus delta of X. For example, if C is 1, this Q is 5. Then the change from 1 to 5 would be 4. So if I say to reach 5, that would be 1 plus 4. C plus delta to X. That's what this represents. Alright. Comma. So this is excuse me, not comma. Minus. Okay. Minus. F of C. Okay. Minus that Y value. So basically what's happening is so if I say this is 1, okay, if I say this is 1 and that point X value is 5, that means the change right here will be 4. So as far as X value concerned, okay, if I take this 1 plus the 4, that will give me my 5. But we are right here, we're talking about the changing in altitude. Changing altitude would be take that 5, the 1 plus the 4, take that 5 and plug into the function that will actually give you a Y value for the Q. So you take the Y value of a Q minus the Y value of the P. Alright, so that will give you the change in altitude. So exactly what is point Q? Well, the point Q actually has an X value of C plus delta of X, comma, the Y value, I'm going to put point Q up here, the Y value will actually become F of, take this X value for the Q, substitute into the function. So that will be F of C plus delta to X. And I do understand this is a little bit confusing because we're using a lot of symbols rather than using actual numbers. Okay, so like I said, just just pretend the C is 1 and this here is 5. So the change will go from 1 to 5 to reach that point. We've got to be 1 plus the difference, which is the 4. Okay, so that's why this X value for another point come from the original X value plus the change in the displacement in the horizontal distance. Alright, so once we establish the X value for the point Q, then whatever that is, we substitute into the function to get a Y value. So the changing in altitude here, the changing in the Y, will be the point Q, the Y value of point Q minus the Y value of point P. That's what these symbols represent. Alright, so imagine this, okay? Once I establish these, once I establish secant line as point, okay, what's going to happen in a minute is as point Q approaches point P, okay, along this curve. I think I have too many black lines, so let me draw my curve as purple. Let me just kind of run over it with the purple. If I want to All right, if I have another point Q, okay, begin to approaching point P, okay, that means I will create more secant lines, okay. Eventually, as the secant line, increase, as the Q approaches the point P, that means the secant line will actually eventually approaches to the tangent line. Okay, but let me just kind of write down the formulas for right now. For this write down the slope for this secant line for a minute. So with all these things going on, remember I basically have 2 points right now. Okay, here's my secant line, crosses the curve at 2 different points. These are my x values and the y values. So we can say the slope m of the secant line, this is the slope of the secant line, got to be, slope of a straight line is y2 minus y1. So we will take the y value of point Q, which is c plus delta of x, minus the y value of point P, which is f of c, divided by the x value of point Q, which is c plus delta of x, minus the x value of P, which is called c. And if I simplify it, c minus c cancels out. All I left with, all I have left with is the top, f of c plus delta of x, minus f of c over delta x, the changing of the x directions. So basically, I'm using the slope of a straight line to actually formulate my slope of the secant line. All right. Let me copy it and bring it down to the next page. Oops, sorry. Alright, so the last point here is saying as point Q approaches point P, the slope of the secant line will also approaches the slope of a tangent line. When such a limiting position exists, the slope of a tangent line will be the limit of the slope of the secant line. What that means is, if you look at the graph, right, this point Q, at that point, you can actually start going towards the point P, the red point. There are infinite number of points on this curve right here. So as point Q approaches the P, if I move this point to here, oops, sorry, let me just draw another point. If the point Q is right here, okay, my slope stays the same. I still have all these same thing, except the numerical values is actually begin to approaching over here. I can have lots and lots and lots of point Q. And every time I draw a point Q, I can actually draw another secant line through point P. Okay. So let's give this a try. It's going to be messy real quick. From point P to the new point Q. That's a secant line. If I will keep on increasing my secant line, eventually eventually all these secant line is going to be the same as what? As the tangent line. That's what I mean as a point Q approaches point P. Okay, the slope of the tangent line will become the slope of this tangent line that I originally draw will become the limits of all these secant lines. Okay, as it approaches to P. All right, so classic, very, very classic example of explaining the limit process. Okay, how calculus is really, how calculus is really come about, the beginning of it. All right, that will conclude this video. The next recording we will talk more about limits. Okay, because limits motivates calculus.